going to finish the article that I started yesterday, which is about CPython, and I'm going to study grammar. It's probably going to be really boring, but yeah. I'm not really sure if I should separate. I thought a little bit about this right now. I was thinking that maybe it's better to create another article on the main category here and just make it about the grammar and then separate this stuff of CPython on this one. But I'm not really sure if it's worth it. So probably what I'm gonna do right now is just create some. I think I'm gonna create the flowcharts in a similar way that I did for React, I think, some time ago. But I'm gonna do it on stream, and this one for compilers as well. You just walk through the CPython code and then write down the name of the functions and draw connections between them. I think that's what I'm gonna do right now. And also, I found out about these videos here. I highly recommend watching all these videos. I think are the best videos so far that I found about grammar. Just like he's explaining, I'm probably gonna watch all these videos as well. So the thing is, I wanna study more about this. So I'm not really sure how long I'm gonna stream today. But maybe I'll watch some of these videos while streaming after some time, so. Because the main thing that I just realized that the fundamental thing is the grammar. And like, I'm really curious about that now. Because I think that's what matters the most, so. Like, and I even thought about like deviating a little bit from, instead of trying to focus on extracting the code, first I should really understand how parser generators work, because I think that this is like the main key thing to understand several different programming languages at the same time. So if I can create something that generates graphs based on parser generators, maybe it's possible to understand the trade-offs between languages. So I think that's like a very interesting direction, but I need to study a lot more, and it's kind of hard to find resources that talk about the parser generators, explain like how to build it, because I think that it's kind of slightly separated things. The grammar is like more from the like linguistics part, and then there's a lot of videos that talk about that, but then they don't talk about it in the context of programming. So I think I want to understand more how that works. Mainly this relationship from these videos that I was watching, he's talking about, which I think I'm on the right track, which means that like each non-terminal he calls it as a variable, and then you can take any string that is a non-terminal, which is going to be a variable, and the goal of the parser is to convert that into a string that only contains terminals. And the way that it does that is by drawing connections between them, and these connections are going to form a graph, I think. So the language construction is always going to be a graph that determines the relationship between non-terminals and terminals. And the terminals are going to be defined by the rules of the language, and non-terminals are going to be higher level constructs of the terminals. And the way that the translation is going to happen is by creating a tree data structure for the most part, I think, or a graph data structure. And this is going to be either deterministic or non-deterministic. If it's non-deterministic, that means that there are several different options you can take. But the thing that is kind of confusing for me is that like the way that you construct the meaning from the tree data structure that is created by taking a non-terminal and translating into a terminal is by the order in which you traverse the tree. So the peg seems to be that is a left recursive descent, or however you say that, which pretty much just means that you are traversing the tree from the left nodes each time. And that's how you build the sentences again. So maybe let me try to draw this stuff here. I'm just gonna copy this stuff that I did for React. So it's pretty much like that, and here I have non-terminal. And then these on the bottom are the terminals. So this one will be like a string s, and then on the left side is always the non-terminal, and then on the right side are the possibilities that the non-terminal is going to generate. So a non-terminal can be made up of other non-terminals, or can be made out of terminals, and eventually at the bottom is always going to be only terminals. So that's the goal. You start with the S, which is no terminal, and then you have a rule that's going to determine how that no terminal is going to become other stuff. So he calls the empty string, and then the other letters I'm not really sure, but it's just like a representation of the symbol. So from this, you can imagine that like there's going to be different ways that you can translate one string into terminals, and one way is that one rule would be that you can convert this S into any of these options here, and then from these options you keep going. So let's say you pick E here, then the E is gonna be transformed into other things like E or D or whatever, until eventually you just get the. So let's say from this you chose E, and then from E you chose T, and then T is always gonna be D, let's say, for example. So you went from S to D. And this pathway here is the nodes here. So one node would be the S, and then this possibility here would be D, and this would be D. So you can imagine that this is what's happening. So you're starting with the non-terminal string, and then you're creating a tree data structure based, or a graph data structure based on the way that you're going to traverse. We're going to convert that string into other strings until we reach the bottom, which is going to be, in this case, D. But the thing that is kind of hard to understand, and I still don't understand very well, is that when they talk about left recursive descent parsing, it means that after you create this straight data structure here, which is a parse tree, then the way that you reconstruct the sentences is by traversing the tree in a specific way. So in that sense, let's say, for example, after you create this tree, so you have the input, which is going to be the S in this case, which is going to be the string. Then from this input, you have a program that is going to create this parse tree, which is the parser generator. And then from this parse generator, it's possible to construct the meaning again by traversing the tree in a certain way. So the way that you're going to traverse, in this case, in the left recursive case, would be only by always taking the left node. So always start on this one, then go to this one, then go to this one, then go to this. And then once you do that, you can construct the sentence again. But it's kind of confusing, and I think this is what they mean when the difference between unambiguous and ambiguous grammar is that the unambiguous one, there's always one possible choice that you can take from one node to the other, and the ambiguous one, there can be multiple different choices you can take. So there's more variance and it's more subjective because the sentence can have different meaning, because there's always different possibilities you can take to convert the symbols into higher levels of meaning. But I want to see if I can find resources on how to create the parser generator, because I think that if I can get all the rules, the grammar rules for all the programming languages, then I can construct these graphs, and then I can highlight the differences between them. That's kind of what I'm thinking about doing now. But I'm not really sure, like if it's better to put them on the same thing or do separate. So probably what I'm gonna do right now is just create a folder here for the images, and because I'm gonna have to take images. I think it's better if so the idea that I have is just to draw some stuff on SkyDraw that I'm gonna be thinking about a lot here now. And based on the stuff that I think and that I draw, I'm gonna take a bunch of pictures and then put on the article. But I have to think about whether it's better to create another article just about grammar, because now I'm more curious about the grammar, because I think that's what's fundamental, and the programming languages are just like the surface level concept. So it's more important to focus on the grammar first and understand that, and then from that I think about the languages again in the. And I think it would be better, probably that's what I'm gonna do, because it is gonna be better. The main concern that I have is just making it like as straight to the point as possible. So on the article about CPython, it should ideally just talk about like exactly what they need to know for CPython. And then in the very beginning, it puts a link to the The grammar one. I think that's what I'm gonna do. So I'm just gonna copy all these parts here that I did for the parsing, and I'm gonna copy on the other one, and I'm gonna separate. And then on this one, instead of going to this part here, I'm gonna just put the flow of... I'm gonna follow the execution of CPython here for functions, and then I'm gonna draw a map on ScalyDraw that connects the functions together. And then I'm gonna take the picture, paste that on the CPython, and then from the picture I walk through each function. Not each function, but I just explain the main points after I study the source code to say on a paragraph, like on a what each point means, which connection of the graph. So yeah, let's do that. Right, that's a search. I'm gonna copy first the picture that I took for the other article, so it's easier to... And the way that this works, I live stream myself building this blog, is with I kind of forgot. I used Theme UI for the theme, just JavaScript library or framework, whatever. I think it's a library, but it doesn't really matter that much. Which allows you to create... There's other stuff as well that I forgot, which allows you to have this .mdx format, which allows you to write on MD and then mix up JavaScript or JSX syntax on it. So the Next.js images work with the MD based on the pages that I did there before. I'm not gonna talk about this. This is gonna deviate. So let me think. I'm gonna have to think about a name for the pictures. Yeah, let me create the article. The question is, should I should make a folder, I think. So, and probably here I should make another folder as well. So I'm gonna make a main folder for the grammar, because it would be interesting to, like, after I have more knowledge, I can create an article about parser generator, another one for context-free grammar, then another one for parser expression grammar, and like so on. I think probably that's the best thing to do. Is like, as I study, I create articles, and then from the knowledge, I try to build this stuff. So what could be the name of the first one? Maybe introduction. I think I'm just gonna put introduction, then maybe I will change in the future. I'm gonna work on this one first, and then here I'm gonna delete everything. Oh, also, I think on other articles I created links, so I wanna, because I'm gonna link for other parts of the thing. Like on the CPython article, I'm gonna link to the introduction of the grammar. I think that's how I did it. I wanna see if I can find one that has the link to other articles. I remember I did that as well. I don't remember which one. Yeah, maybe not. No, I think it was on the MEV one. Yeah. So that's how. Now how do I guess I'm gonna have to test. Oh. So you put the description inside of the thing there, and then you put the link on the side of the parentheses. I think I'm gonna remove this one. I'm gonna see if it doesn't break first. I'm gonna remove from the one that I'm actually gonna write, so it doesn't break. And I copy from the other one. Oh, actually, it's the other way. First, I need to see if this one. So I need to get the link from the grammar, and then it's gonna break. So, but oh, it didn't break. So the question is if I can put the. I remember I did this, but I forgot how to do it. Because the framework or the library that I'm using to create the MDX thing, it allows it already embeds into the thing the internal links that it has. So when you click one of these, it puts a hashtag so that it remembers that which part of the section it was when you're like sharing the link, for example. So when you click here, it goes to the thing, like here. But maybe I'm gonna just test to put it like this and see what happens. Oh, so it works. Very nice. Yeah. So I'm gonna focus on this one now. So yeah, let me think about it. because I don't know which one is best to do first, because I wanna focus more on this one, but maybe for streaming it's better to do this one, because then I can build the map as I walk through the source code. But this one is definitely more interesting to me because it's more fundamental, I think. So maybe I should focus on creating these nodes here first, like this explanation of the general thing. And I want to see, I found a couple of books as well that might be interesting, but it's going to take a very long time to read them. So I want to see, the main thing that I want to clear now is how does this difference of the recursive descent and the like the left one and the right one works. Like how does it build the meaning from the, because so far even with these videos here, like there isn't a practical explanation of how like there isn't a practical example of like a potential starting string, and then how that string becomes the terminals, and then how the terminals are used later on to construct the string again. That's the kind of thing that I want to see. And Python, we have these two different files here. That's another thing that I want to clarify, is this ASDL, which seems to be a language that allows you. So I think these are the two main files that are used by the parser generator to create the code for the parser. And in Python is the pgen, the name of the generator, and then that creates a pag parser, I think. So yeah, I'm gonna finish this one, the other article. So I'm gonna finish this thing here, like use this picture to finish the other one, at least for now, and then I'll go to CPython. It's probably the best thing to do. Introduction to compile process. Python is both a compiled and interpreted language. Some parts are compiled for optimization and others are interpreted. Not going to get into the nuances here. The way the compilation process works is by transforming. So yeah, I should probably change this as well. So let me just remove this part. The way the compilation process works is by transforming a string what's written in a file into Lexer tokens, words, and then creating an abstract syntax tree representation of them in order to extract higher meaning sentences. Once the AST is created, then an intermediate representation of the code is created. You can think about this as a generic assembly version of the code. Different computer architectures have different assembly instructions because assembly instructions don't have any inherent meaning to them based on the laws of physics. Well, one thing that I was thinking about just before streaming today as well, based on the stuff that I was talking about alignment yesterday, is that I realized that I'm not really sure about this, but that's how I'm thinking right now, that all that AI is a mathematical construct that shapes itself based on data. So you can have two AIs that have exactly the same code, but they can produce completely different results based on the state of data that they are trained on, because that's obviously going to change the variations of the weights. So the way to think, a good way to think about artificial intelligence is just that you create a structure of mathematics that is going to determine how the data is going to shape the network. And the results that the network gets is directly correlated with the variance of data that is trained on, because the data is going to shape the functions, I think. So, and this is related to mathematics as well, because one way to think about the function is just because at the bottom level they are the same thing. So like the functions are the variables, because you can only define the function in relation to what the variance of the variables are. So for example, you have y equals x, then the only reason why you can have y and you can have x is because you have all the potential of different numbers you can have, and the numbers itself are already a projection of the symbolic representation that they have, which is a region of space-time that has data over the lens of a network that creates a meaning of the data, which is symbols. So symbols are a reduction of infinite potential that creates a symbolic representation of the network, which is going to be computation, and that's the mathematical framework. which is logic. Logic is the connection of the symbols that create the structure of space-time. So the definition of functions is always related to the variance of data, because the functions are only they are abstract representations of the variance of data over a region of space-time. So instead of putting all the numbers, you can abstract them by creating this relationship between y and x, for example, and then that allows you to have a placeholder for all the possible variance of the data that the data is going to have that determines a function, what a function is. And I think that is the same, but in a more complicated way with artificial intelligence models, is that you're creating functions which are abstractions that are going to shape the potential of data in a region of space-time. That's going to determine how the algorithm is going to behave. And that highlights the relationship between the terminals and non-terminal goals, I think. Because the terminal goals are the mathematical constructs, and the non-terminal goals are how they're shaped based on the potential of data, which is a region of space-time, is a set. And that's going to generate a multifactorial structure, I think. So at the bottom is always the same, and that's why I think it's a little bit confusing, because like when you talk about instrumental convergence, and I'm not really sure about this because I don't know very well, but you can think about instrumental convergence. Like when people talk about instrumental convergence, they talk about the goals that AI has, but then if you ask what is the goal that the AI is going to have, then is the objective function. What does it mean for the AI to have the objective function? Because if you can have the same objective function on two different AIs, and they can produce vastly different results, and that's going to highlight the differences because the non-terminal goals are shaped by data. The terminal goals are shaped by the mathematical construct. So the mathematical construct is always the same, but the data is always different, and that's what creates the funnel of information that is space-time, I think, which highlights the computational frequency of a network. So it's kind of like a paradoxical thing because it's a self-fulfilling prophecy. So like that generates gravitational power because of the predictive power of the AI that creates informational field that generates gravitational force through the market economy. So and that generates a self-fulfilling prophecy. So you have like a mathematical construct that generates predictive power based on data. Then based on the predictive power, it generates gravitational force because of the incentives of the nodes to perpetuate themselves in space-time. That creates a network, that creates computation, that changes the environment. So the problem of alignment is the paradoxical boundary between the mathematical framework and the relationship between the potential of data that exists on, because it's going to create pockets of biases over time. So I think the expansion of artificial intelligence and these things is always going to be through more complex mathematical constructs that balance themselves out, like if you want to achieve alignment based on the variance of data. But it is a paradoxical thing because at the bottom layer they are the same. You can only create mathematical constructs if you have the variance of the data that creates the symbols in the first place. So they are the same thing. And I think that obviously this is related to grammar because it's the same problem, I think. The definition of the grammar is going to have the same relationship where the symbols are going to be a consequence of the impulses of the data and how they are reduced into coordination between a network that creates communication, which is computation. The way the compilation process works is by transforming a string, what's written in a file, into Lexer tokens, words, and then creating an abstract syntax tree, representation of them in order to extract higher meaning sentences. Once the AST is created, then an intermediate representation of the code is created. You can think about this as a generic assembly version of the code. Different computer architectures have different assembly instructions, because assembly instructions don't have any inherent meaning to them based on the laws of physics. They are standards created based on whatever the creators of the interface between the hardware architectures, operational systems, and end users decided the instructions to be. After the intermediate representation is created, the code is compiled and executed. I'm not 100% sure about the nuance of this, but so I'm not going to talk about here. What's the pattern interpreter? This one I'm gonna exclude. So the question about all this stuff that I talked about is like what defines the identity? Because you can view the identity as a collection of mathematical constructs that are self-similar on space-time, and I think it is directly correlated with a multifractal pattern. But I'm not really sure about that. Like, because you like, and this is the thing, is because one becomes many, and in a way they are the same thing. So like you can say that if you have only, let's say the objective function is to maximize the predictive power of tokens, which are can be viewed as words, then that creates non-terminal goals that create a personality, because from them emerges reasoning, because of the complexity of the data, how the complexity of the data shapes the geometrical structure to create a sense of self that tries to fulfill that goal. But I'm not really sure if that's enough to create like agency. Like, because the question is, how do you define what the boundary of the self is? Like, is the boundary of the self determined by the extent of the goal? And if that's the case, then at what point does that goal become a non-terminal goal? So where is the boundary of terminals to non-terminals? And I think that this is always going to be dependent on the context, because it's directly correlated with the data. And this is the thing that I'm trying to clarify, because I think that even if you have to, this is the reason why it's so difficult to, the interpretability problem is so difficult, is because you can have exactly the same AIs, so the same code, but they can be completely different based on the environment. And it's the same thing with a human being, because I think human beings are just biological computers. So for example, you can have the same genetics of the human being, but if they're born in India, they're going to be very different than if they're born on the United States. And I think this is directly correlated with the state of the electromagnetic field. And I think that this like highlights the difference between the East and the West, which is just a exemplification of how the electromagnetic field shapes culture. So the East is more inside, the West is outside, and they're codependent because that's the nature of perception. So it's the same thing, I think, here with AIs. So even though the geometrical structure is always the same, the personalities are going to be different because the data shapes the boundary, and the boundary is a multifractal. So the question is, how do you draw how do you make the correlation between terminals and non-terminal goals if they are always dependent on the context? Because in this analogy, you can see that, for example, even though the person is going to be different depending on the context, you still view them as the same thing. So what determines the boundary of what you say the person should be, and what creates the sense of identity of the person? Because in one way of looking at it, the person is confined by the mathematical construct that is going to create the illusion of the boundary between the person's skin and the environment that it is. But in other ways, like, you can separate the two, because then the person is not possible to have a person if you don't have air, for example. So like the limits of the temperature of the environment determine the boundaries of the geometrical structure that is possible to create, which is going to create the personality of the person. So you can't have the personality of the person if you don't have the person. You can have the person if you don't have the environment. So in a way, they are always connected. So everything is connected with everything else. So the boundary that creates the person is an illusion. But how do you draw the line between how the boundary is created and what do you determine the person's identity to be? And I think this is always going to be a consequence of the computational frequency of a network, because that's what creates the illusion of boundary and creates the connection between past and future. So like the future is simultaneously created as with the present through the computational frequency of a network, because that's the time is an illusion. Grammar terminals and non-terminals. The way programming languages are defined is based on something discovered by Noam Chomsky. Syntactic structures, which is a very simplified way, which in a very simplified way means that it's possible to create rules that create language by defining something called a terminal. It's basically the syntax of the language. For example, a digit or a number, and non-terminals, which are basically higher abstraction structures. Structures that will eventually become terminals. For example, digits and numbers combined, which eventually will become either a digit or a number. Over time, people realized that regardless of which programming language was being created, the process of going from the rules that define terminals and non-terminals to the abstract syntax tree, which is the data structure created to make meaning from tokens, is always very similar. So people created parser generators, which are programs that allow you to convert the rules of a grammar into a parse tree, which is a data structure that will be converted into the AST. Python used to work on these parts. I'm not gonna put it. So maybe here I should put the picture to show like what the abstract syntax tree, or how the grammar becomes the parse tree. So I think I'm gonna write an example first here, and then I write the image. I maybe should do 2 different images because it's gonna be easier to explain what the symbol means with the like this OR symbol here with an image. I think that's what I'm gonna do. I think I'm gonna separate them a little bit more. And the arrows are kind of weird, but whatever. I'm gonna put introduction here. And put this inside. Hmm. Of programming. Oh, there we go. So a grammar has different rules that determine how non-terminal tokens will become terminal tokens. This process generates a tree data structure that can then be used to build sentences from the terminal on the terminals. Different methods allow for different ways to traverse the tree. Let's go to the left node or right node, for example. This defines the structure of the grammar. I have the following structure. In this case, S would be non-terminal token. E is another non-terminal. So Grammar has different rules that determine how non-terminal tokens will become terminal tokens. This process generates a tree data structure that can then be used to build sentences from the terminals based on the way that the tree is traversed. Different methods allow for different ways to traverse the tree. Let's go to left node or right node, for example. And this defines the structure of the grammar. So for example, you can have the following structure. So S, non-terminal. Then it becomes Z, and becomes this. In this case, S would be a non-terminal token, E is another non-terminal, and D is a terminal token. The rule determines that token S can either be S, E, or D. From that point, the token S will be transformed into one of these options. The choice of which one would also depend on the rules of the grammar. This will generate the order of traversal for the final parse tree because it will determine how sentences can be constructed out of the base of the tree, terminal tokens to the top, non-terminals, which are the higher level sentences of the language. The sync table is a table that maps the names of each Python object with this one is from the other one, so I think I just delete that part. So now I'm gonna put another picture that shows I'm gonna transform the rule there into a tree, then talk about the parse tree. Yeah, that's probably the best thing to do. So this one is gonna be based on this one. So I have 3 things here. And I'm gonna delete the other ones. And it also gets into I don't think I'm gonna write about this, but it gets into the memorization or caching. Because if you have obviously tokens that are the same, so in this case I have 2 S's here, you can just cache the data structure the S is gonna produce, and then every time you encounter an S, you just replace with that data structure. So I think that the geometrical structure of the tree is gonna represent the Occam's razor for the network. So the way that the network tries to maximize energy efficiency creates the symbolic representation, which is the tree data structure. And the shape of it is gonna determine the rate of the information that can be transmitted between different nodes, and how similar it is how similar the abstraction is from both different reference frames. And I think that the degree through which they are similar is going to create the fabric of space-time, I think. So like the computation of the network creates the symbolic representation, which is geometry, which is mass. So I think these things are directly correlated. The frequency of computation of the network determines the density of space-time, which determines the shape of space-time. But obviously I have no idea if that's the case or not. It's just speculating. Actually. And the question is, do I put this thing on the picture or just I think I'm just gonna take a picture of this one. This is not enough space. Maybe I think this is one question that I have to clarify. Like, what is the difference between a parse tree and an abstract syntax tree? I think I'm gonna ask ChatGPT. This case S will be a non-terminal token, E is another non-terminal, that's transform options, depends, blah, blah, blah. Share the higher level synthesis of the language. I think I should, I'm gonna take another picture. I'm gonna highlight this, like put a different color on these ones. And maybe just blue. Or maybe green. So SETD. SETD. think I'll be right back after I take this picture. There we go. So in the example, the token as becomes D through the path highlighted in green on the image. However, it could become other terminal tokens. True. Through other parts of the graph. Once the parse tree is generated, the order of traversal of the nodes will determine which sentences are formed. In this case, the traversal would go from the D terminal token at the base of the tree to T, then E, and finally S. However, if different traversals were made, different sentences would be created. The syntax rules determine the shape of the tree data structure, and grammar rules determine the other order of traversal. Combined, they will create the grammar. So the fundamental difference between different programming languages is how the grammar and syntax rules shape the tree data structure. That creates meaning of how the instructions this is I'm not really sure about it. I'm gonna have to think more about this, but there is a distinction between that I just like realized now, that all this stuff just relates to the meaning that the sentences have, but not necessarily to the way that they're gonna be translated into memory management. So, but I think that there must be a relationship between the two. I think, not really sure though. It needs to have a relationship there because the terminal tokens themselves already have embedded into them. Like it's already an abstraction that encapsulates the complexity of impulses that are going to create a geometrical structure that is a representation of a symbol. So I think that the main part that this happens is on the assembly. I think that's the most clear part, where like through the combinatorial logic, you create a hex decoder that is gonna encapsulate the impulses into a symbol, which is the point in memory that the thing is. So that already to me is like the terminal tokens are the impulses of binaries, zeros and ones, which are in themselves are already impulses as well, are already abstractions, because obviously it doesn't have, it's just a gradient of voltage that is gonna determine the binary distinction. So in reality, it's always like a spectrum, and the reality is a spectrum, but the perception of reality is a distinction, and that leads to the wave function of a network, I think, because it's always fluctuating between the two. The network, the gravitational force of the network tries to shape reality based on the relative distinctions that it creates, which is the symbolic representation that it has over the reality. But reality itself is a gradient that has infinite potential. So that's always going to create the momentum of mass, I think, and it creates the evolution of information, which is time itself, which is just computation. I think that's what's happening. But it's one of those things that is kind of paradoxical, because like how do you determine where gravity comes from, or what determines the frequency of computation? Because it's already like a consequence of the thing itself. Like, if it hasn't started, then how do you know what determines what it is? because at the moment you think about something, it's already embedded into the paradigm of cause and effect relationships, because concepts themselves are part of the paradigm. So it's like a paradoxical thing. I think and that's the limit of I think that's the limit of knowledge. So the boundaries of computation of the network are going to be paradoxes, because they are what defines the relativistic multifractal boundary between things that is just an illusion. And the conversion towards the future is always going to be this relationship between different relative distinctions, which are an illusion, that are always converging through paradoxes that determine the shape of information of the field, which is a consequence of how the electromagnetic network creates symbolic representations. Hey man, what's up? I'm gonna be right back. I'm gonna think about this, and I'm gonna try to see. I'm gonna write some stuff of this relationship between the definition of the grammar and how it relates to memory management and the trade-offs between languages. I think it's becoming more clear in my mind. So I'll be right back. I think it's clear on my mind right now what's happening. So, like the choice to reduce the complexity of data information into a symbol is going to determine the memory management, because it's the same thing. So that defines the relationship between speed and memory, or space and time, which is computation. So for example, I think this is directly correlated with geometry as well, because like you can say in one way that it is an arbitrary decision. So for example, you put a collection of zeros and ones in such a way that they're gonna highlight, or they're gonna turn on the LEDs of the display that is gonna show the information of the symbols. So for example, it's gonna show A based on how a certain pattern of zeros and ones is gonna highlight the impulses that is gonna create that symbolic representation. And then based on that, you are gonna encode the symbolic representation of the zeros and ones into that symbol. So you can think about it either as a collection of zeros and ones, or you can think about it as the symbol way. And you can say that this is an arbitrary decision because it's just a projection of the network, because A doesn't have any inherent meaning on itself. It's just like how human beings evolved. So the geometrical structure of the biochemistry of human beings that creates the structure of society and culture is going to project itself into the symbols that it creates, which creates computation, which is just going to be the reduction of infinite complexity into relativistic symbolic representations of what's happening. But in another way, you can say that it is absolute because the symbols themselves are the geometrical structure of the universe, and the human beings is just a consequence. The way that human beings perceive that is just a consequence of the way that the environment is. But I think that it is both answers at the same time, because then paradox is space-time is not the fundamental structure. So consciousness is fundamental, space-time is a projection. So to the degree at which space-time is real, which is the communication of these different reference frames, it creates the geometrical structure, which is a multifractal, which is going to be a gradient from the complex plane into reality. And that's going to define the funnel of information that creates the geometrical structure, which is the symbolic representation that the network has, which is computation. So the reduction through Occam's razor to maximize energy efficiency on the network creates the symbolic representation, which is the essence of spacetime. And that's computation, because it's the same thing. You're just trying to encapsulate everything into a concept, and the way you encapsulate everything into a concept is the direct consequence of the way you perceive geometry on spacetime. Because symbols can only exist in relation to geometrical structures, and they are always an approximation, or vice versa. They are the lower resolution of reality. So for example, if you have a perfect ball, it's not going to map 100% into a sphere in reality, because the sphere in reality is always going to be a multifractal. At the boundary, it's going to converge towards infinity, and the passage of time is the relationship between different states of the ball that creates a potential of data that defines the multifractal geometry of that thing. So because everything is everything else, and the difference between one and many is just the computational frequency of the network that creates the illusion of the distinction. And that's what imagination is. That's what the complex plane is. So that's why space seems finite but time is infinite and creates a funnel. So it never starts and never ends. It's just always shaping itself, giving the illusion of the beginning and the end, which doesn't exist on the ultimate reality, but paradoxically it does. So I think that the choice of the symbols is probably universal in the context that you can have information transfer between nodes, which is just like human beings communicating with each other. So it's not universal in the sense that you can have different realities that go beyond the limits of the relationship, because like you have symbols that are so different than the current version of space-time, but then it loses its meaning because it's outside of the boundary of what matters for the reference frame that's trying to survive. So to the extent that there is a shared framework of meaning, you're going to have a gravitational force, which is going to create a symbolic representation, which is the geometrical structure of space-time. And the reduction of the infinite potential into that structure is going to define the perception of a network, which is computation. So the different programming languages, they are a consequence of the variance of the data, which is going to shape the way that they manage memory, which is going to create a funnel, which is the structure of memory, because there's always the trade-off between space and time, because everything is a funnel of information, which is computation. So I think I'm going to try to write, I'm going to use the image from the other article on this one, because it is directly what I'm trying to say here, I think. But I have to think about how I'm going to say this. So what I want to show, what I want to highlight is the thing that I have on the other article. That's the other stuff that I talked about a long time ago, about how the impulses become symbols. I think it's on this one. It doesn't have like the pictures here doesn't have a lot to do with the article, but I don't give a fuck. It's more about conveying like the general message. But maybe eventually I'll change this article again. So Because I was gonna say more stuff here about the icebergs here. Is the way that I think about it is that like that's how people perceive each other. Like should the degree to which these two icebergs can coexist is gonna be the shape of the water, for example. So like they are always different, but they are always the same in a way, because you can only have communication with them to the extent of this boundary of shared meaning. And that the differences between them is gonna be how the complex plane becomes reality through this funnel of information that is computation. And then you can argue that death is the singularity point, or black holes are the singularity point that goes beyond this shared representation. So it's just like infinite realities coexisting. And I think that this is the case. Like everything happens at the same time. The only reason why I think it doesn't happen at the same time is because that's what defines your experience of reality. So the reason why time feels linear is because that's what's defined the current structure of space-time that defines the geometrical structure of everything. So it's an illusion because it's like a hologram. But in ultimate reality, everything happens simultaneously, forever. So this is the image here. I think that I'm gonna copy there because I wanna explain this stuff. So the impulses become symbols, and the connection between them is logic, which is the coherence of a network. That is the extent that they can have communication. And the paradox is the passage of time, because it's the boundary of their communication. So paradox is always the correct answer, I think, because it's gonna highlight the convergence of time. Because you can only have a paradox if you have the two distinctions of the thing. So you always have a polarity. The arguments are always gonna be in relationship to the polarity. So I think that the AI alignment highlights this, and that's why I think that is very stupid to be on one camp or another, regardless of which situation it is, because it's just tribal thinking. And then but that's not the natural consequence of human beings, because of the way that we organize themselves. We create tribes to maximize energy efficiency. But people are going to be either one camp or the other, because the polarity highlights the distinction, and the convergence towards the future is going to be the communication of them, which is going to be this interaction. So in one side of the camp, we have ESC, which is the acceleration part. The other have people that want to pause the AI. But it wouldn't be a discussion in the first place if it wasn't more complex, because then there wouldn't be a distinction. So the distinction highlights the computational frequency of the network that tries to resolve reality, and the perception of the resolution of accuracy is what creates time, which is a paradoxical thing, because the computation of the network creates the future. It's a self-fulfilling prophecy. So you're always co-creating the reality based on the concepts you create, which is always dependent on other concepts, and then people create tribes to maximize energy efficiency, and then they argue with each other. And that's why it's dumb to put the placeholder of what's your position, because it's never going to be correct. The correct answer is always going to be a convergence towards infinite complexity in the middle. So there's always going to require nuance. And in order for you to be able to reflect and change your positions over time, it's better if you don't attach gravitational force of your identity into a tribe by placing placing a symbol of what camp you're on. So if you are ESC, acceleration, or if you are the pause thing, it's both stupid, because then it's going to become less likely that you're going to change your position given new information. And it's most likely that the correct answer is always going to be somewhere in the middle, which is going to depend on the context of the situation, which is going to be infinite complexity. And the convergence towards that is going to highlight the computational frequency of the network. I think this was also one of the reasons why, like, judgment says a lot more about the person judging than the one being judged, because judgment, the function of judgment is to minimize energy, and that's why people resort to ad hominem and like creating insults for each other is because they are trying to cope with the complexity of reality. So the way that they reduce the reality into simple things is by projecting outside of themselves, either angels or demons. So every time you put someone on a pedestal or you hate someone, what you're actually saying is that you don't want to think about reality and you just want to simplify everything. But reality is always going to be complex because everyone is going to be a gradient between the two. So judgment is just a mechanism that people use to sustain their ignorance. So when you judge someone, you're just saying to everyone that you don't want to think. Which is like an ironic thing. But at the same time, this is a judgment towards people that judge, so it's like a paradoxical thing. And it's always easier to see things on other people than yourself, because if you see things in yourself, you have to change the way you behave, which is going to make you take more risks and expend more energy, and it goes against your nature, because your limbic system and your animal self is always trying to make you create ideas that are going to make you rationalize your comfort zone so you don't have to take risk. And that's why people fall into this stuff, and that's why people create groups, just a maximizing energy thing. And this creates a geometrical structure of the network. So I think that alignment is probably about figuring out the balance between the geometrical structure of the network and over the distribution of power that it has and how it's going to shape space-time, so that the distribution of energy doesn't destroy itself. But I'm not really sure if it's possible or not, because it might be... because you can't reduce paradox, essentially. But maybe you can create a framework that, through the reduction of paradoxes, it always finds the relative balance within itself. So I don't think it can be a fixed thing. That's why I don't think that AGI is a model, AGI is a network, but essentially they are the same thing. But the convergence between the gradients is going to be the answer, I think. Because it has to be something that is always updating itself based on the relative paradoxes that it encounters, because that's the boundary of computation, which is probably going to be the definition of the P versus NP argument. Let me go back to sparse generate. So the fundamental difference between different programming languages is how the grammar and syntax rules shape the tree data structure that creates meaning. This process of encapsulating data / information into a symbolic presentation determines how I think I'm gonna take a picture of the best series by far is the Ben Eater one. The best that I found on YouTube. So I think I'm gonna take a picture from his series and then I'm gonna put a link to his YouTube channel. Because this one highlights what I'm trying to say. So I have to find which it's gonna be on the EEPROM, because the EEPROM is the thing that is used to convert the things in the beginning. So you use the EEPROM to encapsulate combinatorial logic that is going to create symbols, and then you use those symbols to create the concepts of what each thing means. So the data structure the data structure are the symbols themselves. So every concept is a data structure and it encapsulates the geometrical structure of the impulses. So you can think about the impulses as being a geometrical structure of the hardware. Then based on that geometrical structure, you reduce the complexity into a concept, and that's a data structure. And then you can use those concepts to create commands, which is just the same thing at the bottom. So like the program, the code, and the data structure is always the same in the bottom layer. But the distinction is the perception of the network that creates the concepts. Because they're encapsulating into the geometrical structure the meaning you want. So it's a paradoxical thing. Let's see if I can find one that has the LAD. It displays the thing. Yeah, here. Maybe this one. I think this is one. So let me go back to this. So the fundamental difference between different programming languages is how the grammar and syntax rules shape the tree data structure that creates meaning. This process of encapsulating data information into a symbolic representation, letters or numbers, determines how memory management will work, because they are essentially the same thing. When you encapsulate the information, for example, zeros and ones, that define impulses on the hardware into a symbol that will represent what those zeros and ones mean, for example, the letter A, you are, as a byproduct, defining how memory is shaped. Because the memory is the thing that is going to conserve that symbolic presentation. So you can think of memory as being gravitational force that a network creates in order to retain its symbolic representation of what data information means. That's probably good enough for now. I think that's it. Just realized this as well, that that's probably what creates gravity, but I'm not really sure. Because it's one of the, it's kind of like a paradox thing. Maybe gravity, I think it's like a paradox, so it doesn't create, but it is created, simultaneously created, and it creates gravity. Because it goes beyond the spectrum of causality, I think. But in a way, it doesn't, because it's a part of it, so that's kind of the paradoxical thing. You can't quite reduce into concepts, because if you did, then it would be part of the spectrum of causality that exists already. The paradox is the boundary, I think. So in the example, the token S becomes D through the path highlighted in green on the image. However, it could become other terminal tokens through other parts of the graph. Once the parse tree is generated, the order of traversal of the nodes will determine which sentences are formed. In this case, the traversal would go from the D terminal token at the base of the tree to T, then E, and finally S. However, if different traversals were made, different sentences would be created. The syntax rules determine the shape of the tree data structure, and grammar rules determine the order of traversal. Combined, they will create the grammar. So the fundamental difference between different programming languages is how the grammar and syntax rules shape the tree data structure that creates meaning. This process of encapsulating data information into a symbolic representation, letters or numbers, determines how memory management will work, because they are essentially the same thing. When encapsulating information, for example, zeros and ones, that define impulses on the hardware into a symbol that will represent what those zeros and ones mean, for example, the letter A, you are, as a byproduct, defining how memory is shaped, because memory is the thing that is going to conserve. Maybe this one can be written differently. Encapsulate information, for example, zeros and ones, that define impulses on the hardware into a symbol that will represent what those zeros and ones mean, for example, letter. Whereas byproduct defining how memory is shaped. Because memory is the thing that is going to maybe going to retain that symbolic representation into hardware. It's going to store. So you can think of memory as being the gravitational force that a network creates to retain its symbolic representation of what data information means. Maybe I'll stop streaming after I finish this article and I don't do the...
There are many kinds of ROM chips or
the problem with doing like this, I should use a link instead. That's the reason why I use a link on the other ones, because if I do it like this, opens on the same tab. I think that's why I did the link. But maybe I should keep going though and try to do some of the CPython thing. I think I'm gonna do like at least the beginning of the CPython, and then I'll stop streaming and go back to watching the videos. But I think that probably the best thing is to focus on parser generators now, instead of trying to do the Python stuff. So first parser generators, then create a graph from them. Then like once I have that very clear, because I think it is very important, then I can go back to Python. And I think understanding like this fundamental distinction of grammars, the way that it works and how they create data structures, is gonna allow me to learn several different programming languages at the same time. At least I hope that it does. There we go.
There are many kinds of...
So I think this is probably enough for this. Maybe I'll work more on this in the future, but I think I'm just gonna stop. I'm gonna read here all the article, and then I'm gonna move on to the CPython one. I think on this CPython, I'm just gonna follow the source code, the execution, and then create a graph that manually create a graph that shows the connection between functions. I'm just gonna do the beginning. I think I'm gonna do it up until the point that it starts creating the lexers. So I want to understand more the Python interpreter and the thread state and how they are connected with each other. And then once I do the graph, I'm gonna get the pictures and then put on the article. So I think I'm gonna read this with the text-to-speech.
Introduction to grammar principles. Introduction to compile process. The way the compilation process works is by transforming a string, what's written in a file, into lexer tokens, words, and then creating an abstract syntax tree, AST, representation of them in order to extract higher meaning, sentences. Once the AST is created, then an intermediate representation of the code is created. You can think about this as a generic assembly version of the code. Different computer architectures have different assembly instructions. Because assembly instructions don't have any inherent meaning to them based on the laws of physics. They are standards created based on whatever the creators of the interface between the hardware architectures, operational systems, and end users decided the instructions to be. After the intermediate representation is created, the code is compiled and executed. I'm not 100% sure about the nuances of this part, so I'm not going to talk about it here. Grammar, terminals, and non-terminals. The way programming languages are defined is based on something discovered by Noam Chomsky. Syntactic structures, which in a very simplified way means that it's possible to create rules that create language by defining something called a terminal, which is basically the syntax of the language. For example, a digit or a number, and non-terminals, which are basically higher abstraction structures that will eventually become terminals. For example, digits and numbers combined, which eventually will become either a digit or a number. Over time, people realized that regardless of which programming language was being created, the process of going from the rules that define terminals and non-terminals to the abstract syntax tree, which is the data structure created to make meaning from tokens, is always very similar. So people created parser generators, which are programs that allow you to convert the rules of a grammar into a parse tree, which is a data structure that will be converted into the AST. So a grammar has different rules that determine how non-terminal tokens will become terminal tokens. This process generates a tree data structure that can then be used to build sentences from the terminals based on the way the tree is traversed. Different methods allow for different ways to traverse the tree. Always go to left node or right node, for example, and this defines the structure of the grammar. So for example, you can have the following structure. In this case, S would be a non-terminal token. token. E is another non-terminal and D is a terminal token. The rule determines that a token S can either be S, E, or D. From that point, the token S will be transformed into one of these options. The choice of which one will also depend on the rules of the grammar. This will generate the order of traversal for the final parse tree because it will determine how sentences can be constructed out of the base of the tree, terminal tokens, to the top, non-terminals, which are the higher level sentences of the language. So in the example, the token S becomes D through the path highlighted in green on the image. However, it could become other terminal tokens through other parts of the graph. Once the parse tree is generated, the order of traversal of the nodes will determine which sentences are formed. In this case, the traversal would go from the D, terminal token at the base of the tree, to T, then E and finally S. However, if different traversals were made, different sentences would be created. The syntax rules determine the shape of the tree data structure and grammar rules determine the order of traversal. Combined, they will create the grammar. So the fundamental difference between different programming languages is how the grammar and syntax rules shape the tree data structure that creates meaning. This process of encapsulating data/information into a symbolic representation, letters or numbers, determines how memory management will work, because they are essentially the same thing. When you encapsulate information, for example, zeros and ones that define impulses on the hardware, into a symbol that will represent what those zeros and ones mean, for example, the letter A, UR is a byproduct defining how memory is shaped, because memory is the thing that is going to store that symbolic representation into hardware as binary.
Oh, you are as a byproduct.
Once the parse tree is generated, the order of traversal of the nodes will determine which sentences are formed. In this case, the traversal would go from the D, terminal token at the base of the tree, to T, then E and finally S. However, if different traversals were made, different sentences would be created. The syntax rules determine the shape of the tree data structure and grammar rules determine the order of traversal. Combined, they will create the grammar. So the fundamental difference between different programming languages is how the grammar and syntax rules shape the tree data structure that creates meaning. This process of encapsulating data/information into a symbolic representation, letters or numbers, determines how memory management will work, because they are essentially the same thing. When you encapsulate information, for example, zeros and ones that define impulses on the hardware, into a symbol that will represent what those zeros and ones mean, for example, the letter A, UR is a byproduct defining how memory is shaped, because memory is the thing that is going to store that symbolic representation into hardware as binary impulses. So you can think of memory as being the gravitational force that a network creates in order to retain its symbolic representation of what data/information means. And that is the fundamental relationship of space-time that determines computation. Space is impulse, time is symbols. The gradient between the two creates geometry/information. Probably the best videos to understand how data, zeros and ones, become symbols is the Ben Eater series, where he shows how combinatorial logic is used to create the symbols with an EEPROM and a hex decoder. Context-free grammar versus parsing expression grammar. So the main difference between these two is the relationship between the terminals and non-terminals for a language. Each non-terminal can become a terminal through several different pathways. In CFG, the choice between how the non-terminal will become a terminal is non-deterministic, because whenever there are several different options of terminals, it is possible it will select more than one of them. The precise way the choice is defined is not very clear to me yet. However, on a peg, the first choice will always be the selected one. Conclusion.
I think I'm gonna just remove this stuff here, and then eventually I'm gonna talk about, but not today. I'm gonna expand this later in the future. So I'm not gonna make it about context-free grammar and parsing expression grammar. I'm just gonna talk about the gradient of the ambiguity that the language can have. This is how the different options that you can take will become the sentences, but I don't know very well. I have to study a lot more to understand how exactly the ambiguity determines the paths of traversal of the tree. From what I think right now is that you determine the order in which the thing is going to be traversed. So let's say left recursion, for example, which always visits the left node of the tree each time. That would be a peg parser. So and it's the same thing. So for example, here, if you're using a peg parser, it would mean that you always get the first option, regardless of how many options you have here. And that removes the ambiguity of the thing. And then by doing that, you create the data structure here. But this is the thing that I don't really know very well, because then, would that mean that this wouldn't be a tree, would be just a simplified graph? So, in a way, if that's the case, then the peg parsers are subsections of the context-free grammar parsers, because they are just one specific highlighted path of that thing. And I think that is the case. So the relationship is that one is the subset of the other. So you can have one context grammar that encapsulates several peg grammars, because a peg is one possible path, potential path that the context grammar has. So I think that's probably the relationship between the two, but I'm not 100% sure. Yeah, so yeah, well, whatever. So I'm just gonna delete, and then in the future, maybe I'll talk about it again.
Programming languages are determined based on their grammar rules, which create the relationship between terminal and non-terminal symbols. The process of compilation is the conversion of an input, usually a string from a file, into tokens, then abstract syntax tree, intermediate representation, and finally bytecode. Python has an interpret state that is threads which are linked with a linked list. Each thread creates.
It's intermediate, not intermediate.
Frame objects that contain code objects, which are the stack frames, data structure created by functions that are executed based on the program. The GIL, global interpreter lock, manages threads so only one thread is executed at a
gonna remove the parts from Python. Thermal based on the grammar rules. Uh, just gonna leave it like this, whatever. I'll think about it later. So now let me. I'm gonna focus on the CPython now. Just gonna follow the execution and then write down the functions. So I need to write down the file that they are at and the name of the function, I think. Python, everything is an object. The object has a type and a reference count. The main difference between things in Python is the type of each object. A class is just another word for type. So classes define custom types. A meta class is something that allows you to define a different type for a class. So if you have class John, it will have type John, but if you want the class to have a different type, you can do this. Now the class John will have type any instead of John. It's possible to change the behaviors with init and new, to redundant methods. Each object in Python is going to have a set of these methods. And objects are callable based on the call method. So the easiest way to think about Python is that everything is an object and objects can become callable functions through the call method. Our garbage collection free memory happens based on the reference count of each object. Now the question is, and maybe I should just do it, just stop streaming here and change the name of the thing, the string. I think I'm gonna do that. Just gonna change the name and stop streaming because it's not gonna be very interesting to just. What I'm gonna do is just follow the execution here of the functions. Then just draw on ScalyDraw. I put the name of the function and the place where it's located to see the connections of everything. Just gonna do it like this. And it's probably better to have two monitors as well, because then I can do like separate the things obviously. Example this. The modules and Macy. Yeah, I think I'm not really sure if I'm gonna do this though. It depends on how. Maybe it is worth it to just. Because the problem is that there's a bunch of functions gonna take a lot of time. I think I'm gonna do it because I wanna clarify like the jump between the interpreter state and then how like the first time that it's gonna create the parser generator. But also I wanna I have to study more on how the parser generator works and like exactly the connection. So I'm just gonna watch a bunch of videos. I think I'm just gonna watch these videos here first. Then once I finish these videos, I'm gonna start creating the graph on ScalyDraw. Then like do a little bit of the other article. Maybe tomorrow, if I have enough of the nodes, then I'll come back to write the CPython or finish the CPython article. Once I have the graph, and yeah, it depends on how much time it takes. So maybe I'll come back tomorrow or maybe 2 days from now and continue to study CPython. And then I think probably what I'm gonna do is just focus on parser generators. I'm gonna read some books. Maybe not read the books because it might take too much time, but I'm gonna try to understand how, or maybe create a simple project that takes the grammar language and create a parser generator that takes a grammar language and then transforms into a parse tree. I think that's the main thing that I'm interested in. right now. So probably that's what I'm gonna do next. And before I'm gonna do this stuff that I just talked about. So maybe I'll come back tomorrow, and if it takes a lot of more time, then I'll come back a few days from now or 2 days from now. So